Hello and welcome back to the Maths Behind the Economics YouTube channel. This is the series where we investigate logarithms for economics, and today's video is the 10th in the series, and we will be concentrating on how to work with exponents behind the logs. Remember a couple of videos ago we have listed all the different logarithm rules, and now we're going through them one by one and showing how they work and then also discussing the former proofs. So first of all, I'm going to introduce you the rule again, this specific rule. Then we will discuss why the rule works, and as always, we're going to look at some examples. Let's get started. So here are the rules. Well, if I have some log with base b, generic log base, and behind that log I have got some number raised to an exponent of n, then that is going to be equal to that exponent brought in front of the same log. Special case of it when we use the natural logarithm of ln. So ln x to the n is just going to be equal to n times ln x. But there is a slightly different version of this rule again. If we have got a log base b, so again just some generic base b, but behind that log sign now I have 1 over some number to the power of n or exponent of n, then that can be replaced as negative n times the same log. So if the exponent is in the denominator, 1 over some number to the power n, then this power will be multiplied out but with a negative number in front. So it's going to be negative n rather than positive n in the original version when it was just x to the n behind the log base. And again, as always, the special case is what happens when we replace the base with ln or natural logarithm, which is very, very common in economics. So ln of 1 over x to the n is going to be equal to negative n times ln x. Again, we mustn't forget that when we're talking about the base, it always have to be bigger than 0, and on top of that, the base can't ever be equal to 1. And what's more, that the number in the argument, our x, is always have to be also a positive number. However, in these rules, we have got an extra number of n, and for that, in this case, it's going to be a positive whole number. Okay, so let's make some more space and try to have a look at some examples and see whether this is actually holding. So we need to see whether log base 3 4 to the 5 is going to be equal to 5 times log base 3 4. Well, what we're going to do here is just apply the definition of the exponent. And if you don't remember that, we have got a whole exponent series, and I'm going to link you the first video where we discuss the definition of the exponent, so you can remind yourself. So basically then, behind the log sign, I can write 4 times by itself, 5 times, 1, 2, 3, 4, 5 times. But now, what I've noticed that there is multiplications behind the log sign. So I can repeatedly apply the multiplication rule, which we discussed in video 8. So now I can replace this expression by log base 3 4 plus log base 3 4 plus, as you can imagine, it's a little bit boring to write it all out, but we have to write it out 5 times, so I need to write it out 2 more times. Log base 3 4 plus log base 3 4. Now, what's important here is that I'm adding the same thing together 5 times. Well, that's lucky, because adding the same thing repeatedly is the same as multiplication. So this is basically just 5 times the same thing, which in our case is log base 3 4. Voila! We demonstrated that the rule holds in the case of base 3, argument 4 and power 5. Well, we just demonstrated one example. Let's see if this holds if we looked at a slightly different example. So what happens if I have got log base 2, 3 to the 4? Well, let's follow through with the same logic. So, applying the definition of the exponent, we can replace 3 to the 4 by 3 times 3 times 3 times 3. So I'm multiplying 3 by itself 4 times. But then again, repeatedly applying the multiplication behind the log rule, then we can replace this by log base 2 3 plus log base 2 3 plus log base 2 3, and one last time log base 2, 3. Let's just make sure 1, 2, 3, 4. Yes, it's 3 to the 4. Now, again, applying the same logic, I'm adding the same thing together a repeated number of times, specifically 4 number of times. So this whole thing can be replaced by 4 times the thing I'm repeatedly adding, which in this case is log base 2, 3. Okay, so we've seen 2 examples. We seem pretty convinced that this works. But as always, we need to make sure that we follow the former procedure and we do the former proof. So this is not just some example when it holds, and we can accidentally come across an example when it doesn't. So let's make some more space. And then let's properly investigate why this rule works all the time. So again, let us state the assumptions. Let us state what numbers should it work for. So with the logarithms, we always have to make sure that the base is a positive number, and what's more, the base cannot be equal to 1. We discussed it in details. If you don't remember, go back and watch video 2, because it's very important that you understand why the base have to be a positive number and why the base can't be equal to 1 ever. What's more, we also discussed in that very same video that the argument has to be a positive number, and because in this case we have got another number, we need to make sure that this number n is going to be a positive whole number. Now that we've done the groundwork, let's have a look how the proof goes. Well, we've got a log base b, which can be any positive number except 1. And then we have got a positive argument that's raised to a positive whole power. So just like in the examples above, we're going to follow same logic. So we're going to keep the log same base, but now we're going to apply the definition of the exponent. So that's basically x times blah 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 x, not forgetting that we do this n times. But then again, what we can do, now we can apply the log multiplication rule. I'm just going to call it log mult. So we remind ourselves that this is the log multiplication rule, basically the rule where there is a multiplication behind the log sign. And we're going to apply that repeatedly. And by that, what I mean is that I can replace this log bx plus log bx times x times x, but now I would have it n minus 1 times. And then I keep doing this, and eventually I'm going to end up with log base x plus log bx plus log bx, and again I had it now n times. And again, now we just need to remember that if we repeatedly add the same thing together a number of times, that is exactly multiplication. So we have got n log bx's that we're adding together. That's the same as if I was to multiply n and log bx together. And voila, here is our rule. Now remember, because we are working with economics and mathematics for economics, it's always nice to see how these rules work with the natural log. So let's make some more space and then write out this same rule for the natural log. So if I had ln x to the n, then that's just going to be ln x times x times x, which then I can rewrite it as ln x plus ln x plus ln x, which is again, because it's n times, just like the same way in here, this is also n times, it's going to be n times ln of x. Actually, I didn't need to write this out because I just remember that ln is basically equivalent to log e base, so I can apply the generic rule when b is replaced with e. And because e is a positive number that's not equal to 1, it fulfills the criteria for the proper base in the log, and therefore that rule, the log b x to the n, has to hold for e as well. Now, let us make a little bit more space and let's move on to a slightly different version of the same rule. So again, let's make sure that we lay the ground properly first and establish what numbers we're working with. So let b be a positive number that is not equal to 1, because that's going to be our base. Let x, the argument, be a positive number, and let n be a positive whole number. Then we claim that log b 1 over x to the n is going to be equal to negative n log b x. Okay, let's have a think about what's going on in here. Well, our starting point is the log b 1 over x to the n. Well, I've noticed here that there is a division behind the log sign, so I can apply the log division rule, and I can replace this by log b1 minus log bx to the n. If you don't remember why this rule works and why this rule is true, then I suggest that you check out our previous video, video 9 in this series, where I have shown you the general case and plenty of examples of how to use this rule and why this rule works. What's more, from video 5, hopefully you remember that this is nothing else but 0 in disguise, because remember, any base raised to the 0 is always equal to 1. Again, if you don't remember, go and check out that video as well. So I can replace this by 0 minus log bx to the n. But we have already shown that log bx to the n can be replaced by n times log bx to the n. So 0 we don't have to write out, the negative sign I need to keep, and then I can just replace log bx to the n by n times log bx. And that's the special case. Well, if you know your exponents well enough, then you might have spotted that I could replace log b 1 over x to the n by log bx to the negative n. And we just demonstrated that this is equal to negative n to the log b of x. Now that begs the question, can I just bring down any kind of numbers from the exponent in front of the log sign? Well, we have to wait for the next video to properly introduce that, because for our case, it only works if n is a positive whole number. So for now, let's just keep that in mind. And before we go on to the practice questions, let's just state what this version of the rule would look like if we were to use the natural logarithm. Okay, let's make some more space. And then if we had ln of 1 over x to the n, that can be always replaced by negative n times ln x. And again, this rule holds because it's a special case of the above rule when we replace b with e. So the base is now not just a generic base, but the specific base of e. Right, let's go on to the practice questions. And our first question will be log base 3a plus log base 3a cubed minus log base 3 4a squared. What can we do here? Well, first of all, we notice that there is a 3 in the power in here, so I can bring that power down in front of the log sign. And I've also noticed that there is a power here in the 2. However, the a is multiplied by 4, so I cannot simply apply the rule. I have to break this multiplication into separate log signs first. So let us do just that. So the first term, log base 3a, stays as it is. There's nothing I can do with this. The second term can be replaced by 3 times log base 3a. And the third term I can break into 2, and I have to keep it into a bracket because a negative sign applies to this whole log 3 4a squared. And I can break it into log 3 4 plus log 3a squared. And again, why did I do this? I did this because I wanted a squared on its own, so I can apply the rule of bringing the power down in front of the log sign. Okay, so keep going. I've got log 3a plus 3 times log 3a minus log 3 4. And when I'm applying the negative sign, I have to apply that to everything inside the bracket. So minus log 3 3a squared as well. Okay, so I've got 1 log 3a plus 3 log 3a. That means 4 log 3a in total, minus log base 3, 4. Remember, I know the base here, I know the argument here. So this is just a number in disguise. It's not a whole number because 4 is not a whole number power of 3. Nevertheless, this is still a number which I can replace by its value if I wanted to use the calculator. However, because this is most likely going to be a never-ending, not repeating decimal number, I will lose some value if I was to do the rounding. So for now, I'm going to keep these numbers in the log form because those will be exact numbers rather than rounded versions. Okay, so we got one more term, and for that we can bring the 2 down in front of the log sign, so this is now going to be minus 2 times log 3a. Okay, now what's happening in here? I've got 4 log 3a and I've got negative 2 log 3a. So I've got 4 times something minus 2 times the same thing. That's altogether just going to make it 2 log 3a minus log 3, 4. Okay, so that was practice question number 1. Let's make some more space, quite some more space, and go on to the second practice question, which is 5 log base 2x plus log base 2y. Well, I'm going to use this practice question to demonstrate that you can apply the rule both ways. What I mean by this? I mean by this that you can bring down the exponent from behind the log sign as a multiplier at the front of the log sign, or you can bring up the multiplier from front of the log sign into an exponent behind the log sign. So I can replace 5 log 2x by log 2x to the 5th plus log 2y. Why is it good for me? Well, it's good for me because now I've got the same log bases with an addition between them. So this can be replaced by a single log sign and x to the 5 times y as the argument of the log. Sometimes you might want to break out a log with a complicated argument into simple logs, or you might want to make a log with a complicated argument as sums and differences of logs with individual arguments. It will always depend on what you're trying to achieve with your calculations. Okay, move on to the next example, and it wouldn't be an economics video if we didn't use a natural logarithm question. So let's look at what we can do with ln x over 3 plus 2 ln y minus ln root x. So what I've noticed is that there are same log bases, because the log is ln in each of them, so it's the e-based logarithm, but this 2 is in my way. I cannot apply the addition and the subtraction rules because there is a 2 in here. So what I need to do first, I need to bring that 2 up into the exponent. So this is going to be ln x over 3 plus ln y squared minus ln, and I'm going to replace root of x by x to the half. And now I can apply the log addition rule in here. So the first 2 terms can be replaced by ln x over 3 times y squared minus ln x to the half, which means that I can apply the log subtraction rule. So when there is a subtraction between the same log bases, that can be replaced as the division. So ln xy squared over 3. Remember, when I multiply a fraction with a whole number, I don't know the value of y squared, but that's going to be some sort of whole number because it's not a fraction. That's just multiplying the numerator. So that's why it can be replaced by this. And remember, when you divide a fraction by some number, effectively what you're doing is you multiply the denominator. So I can put down x to the half into the denominator. Let's tidy this one up a little bit, because what I've also noticed is that I have x in the numerator and I have x in the denominator. So my knowledge of exponents comes handy all the time. So how can I simplify x over x to the half? Well, I need to remember that when I'm dividing the same bases, I subtract the powers, and I need to remember that x is always x to the 1. So that's going to be 1 take away a half. So that's just going to give me x to the half, but up in the numerator. So this whole log sign can be replaced as ln x to the half y squared over 3. Well, you can argue whether this is a simpler version or not than the original version we started with, but I think you agree with me that we have demonstrated quite some understanding of how to manipulate these logs. Next question, question 4. Log base b x y to the 4 over cube root of z. Now, what we're going to do here is go backwards. We have got one log base with a complicated argument, so we're going to break it out into multiple logs of the same base and addition subtractions between them. We have got a division behind the log base, so first of all we can apply the log division rule, and I'm going to write here log div, so we know what we do. And then this can be replaced as log b x y to the 4 minus log b cube root of z. Then next, I can apply the log multiplication rule, log multiply, because there's a multiplication between x and y to the 4. So log bx plus log by to the 4 minus log b cube root of z. That's going to be equal to, again, what I'm going to do now, I'm going to use the log exp rule. What happens when we have got an exponent behind the log sign, which is the rule that we discussed today? The first term does not change, that stays as log bx, but the second term can be replaced as 4 times log by, because remember, the exponent can be brought down in front as a multiplier. And I'm going to keep minus log b cube root of z. Now, you might remember that cube root of z can be replaced by z to the 1/3, but remember in the rule we only discussed what happens to exponents if the exponent is a positive whole number. 1/3 is not a positive whole number. But rest assured, we'll discuss this case in the next video. Okay, more space, and then look at the last question. And again, we're going to return to the natural logarithm base, so ln 4th root of a b cubed all over z squared. Again, what we're going to do is going to break this complicated argument into multiple log signs with single arguments. So first of all, we're going to again apply the log division rule, and we're going to replace this as ln 4th root of a b cubed minus ln z squared. Then we're going to apply the log multiplication rule, and we replace the first term with ln 4th root of a plus ln b cubed, and the last term stays as negative ln z squared. And now we're going to apply the log exponent rule. Basically, what happens if we have got an exponent behind the log sign, because we have got two exponents behind our log sign. So again, the first term stays as it is, ln 4th root of a, because we still don't know what to do with the root behind the log sign. That's going to be the next video. But the 3 can be brought down in front of the log sign, so that's going to be 3 ln b. And the 2 can be brought down in front of the log sign, and that's going to give me 2 ln of z. Well, I hope you liked the video today. I very much hope that you learned something new, and that you now fully understand why you can bring down numbers in front of the logs when they are in the exponent of the argument. In the next video, we're going to extend on the work that we've done today, and we're going to discuss what happens when we have got roots behind the logs. I hope to see you there. Have a good day. Bye.